This is Bappaditya Chakravarti here, and you are watching YouTube channel Chemistry for Neet. Today we are going to discuss the topic in organic chemistry, and this is electrophilic substitution reaction. Now, what is an electrophilic substitution reaction? An electrophilic substitution reaction is that where the substituent is an electrophile. Now, what is electrophile? In English, phile means love or attraction. So, the species which has attraction towards a nucleus means positive center. So, which has attraction towards nucleus or a positive center is called an electrophile. So, benzene, one of the hydrogen atom of benzene gets substituted by an electrophile. The reaction is called electrophilic substitution reaction. Now, electrophile that must carry because it is getting attracted by electron or negative charge. So, an electrophile must have some positive charge, or an electrophile is an electron deficient species. Now, let us see what happens when an electrophile gets attracted by benzene. Why an electrophile is getting attracted by benzene? Benzene, what is a benzene? You know the structure of benzene. Benzene is simply a planar structure. Benzene has a planar structure where all the 6 carbon atoms of benzene, which all are sp2 hybridized, lie on a same plane, and all the carbon atoms are sp2 hybridized, and 6 carbon atoms are there. 6 carbon atoms are there. 1 2 3 4 5 6. So 1 2 3 4 2. Now all carbon atoms are sp2 hybridized, that is all carbon make 3 sigma bond with 2 carbon atoms and the other with a hydrogen atom. Okay, so all these carbon atoms are sp2 hybridized, and each carbon contains a unused pi orbital, and that pi orbital is, if the bond axis is x-axis, if we consider the axis is x-axis, then the unused orbital or pz orbital that will be present in parallel. Okay, or all the pz orbitals are parallel to each other. All the pz orbitals which are unused are parallel to each other, so they can make a lateral overlapping. So here a lateral overlapping occurs, and that occurs in alternative carbon with the alternative carbon atoms. Okay, now that lateral overlapping which results to pi bonding, this overlapping are not, the extent of overlapping is very poor. In case of sigma bonding, the head-on overlapping, the extent of overlapping is very high. That's why the resultant sigma bond is very strong. But in case of a pi bonding, lateral overlapping, the extent of overlapping is very poor. That is why those bonds are very weak. So we can consider as all the 6 carbon atoms are present in a plane, and above the plane and below the plane some pi electrons are there, and those pi electrons are not tightly held by these carbon atoms. That's why if there is some positive center in the vicinity of benzene ring, that pi electrons can easily get attracted towards the positive center. Okay, so that is how electrophilic substitution of benzene occurs. Now let us see what happens when an electrophile comes in the vicinity of a benzene ring. Let us see the mechanism of electrophilic substitution reaction of benzene. So this is benzene where alternative pi bond and sigma bonds are there, and this one is an electrophile. As I said earlier, that an electrophile, electrophile means love or attraction. So electrophile, that has attraction towards a negative center, electron or negative center. So it must carry a positive charge, or an electrophile is an electron deficient species. Now when an electrophile comes in the vicinity of a benzene ring, as we see, the pi electrons are above and below the plane of the benzene ring are not tightly held by the carbon atoms. Therefore these pi electrons can easily get attracted by this positive charge or by this electrophile. So if pi electrons comes to bond with this electrophile, say if the bond breaks by this manner, the bond is still bonded, the bond is still there with this carbon atom but breaks from this carbon atom. So the pi bond breaks from this manner, and the result is that the other two pi bonds remain intact here, and a hydrogen atom is already there, and electrophile comes. So one goes to the above the plane, and the electrophile goes to above the plane, as if two groups, hydrogen and the electrophile, present in the same plane, there must have some we say steric hindrance. Now to avoid the steric hindrance, one goes to above the plane and the other goes to below the plane. Now the bond breaks from this carbon atom, therefore it must contain a positive charge. Okay, now there is a stabilization, and that stabilization is via resonance. What happens then? To reduce this positive charge or to neutralize this positive charge, this bond breaks from this carbon atom and attached to this carbon atoms, that is the pi bond shifts from this carbon to from here to there to form a resonating structure. Okay, so here a pi bond comes and the bond breaks from this carbon, so the positive charge comes here, that remains intact, and those electrophile and hydrogen atoms also remain same. Next, the next resonating structure, what will be the next resonating structure? If that pi bond comes from here, then the other resonating structure forms, and that is the bond breaks from this carbon, so positive charge comes here, and the pi bond formed between these two carbon atoms that was present already, and those electrophile and hydrogen atoms. So these are the three resonating structures we can draw. We can't draw anything above this. So three resonating structures that makes this carbocation stable. So all these carbocations are, we can say, resonance hybridized. Okay, so the positive charge actually remains from this carbon to from here to there. So the overall thing is that the positive charge lies between this carbon atom to this carbon atom. So this is the overall picture, and it is called the sigma complex. So this is called sigma complex. Okay, now what happens? Now hydrogen here releases as by giving the bond pair electrons to this carbon and removed as H plus ion, and here the electrophile comes. So here hydrogen atom was there, and now the compound form is carrying the electrophile. So the electrophile actually replaces the hydrogen atom. That is why this reaction is called electrophilic substitution reaction of benzene. Now the electrophilic, the overall reaction mechanism is same. Now here some example of electrophilic substitution reaction. First of all, we will consider about the FRIEDEL reaction. Now what is FRIEDEL reaction? If you want to enter some alkyl group into the benzene ring, then you may use the reaction which is called FRIEDEL alkylation reaction. Now if you enter a methyl group, if you want to enter a methyl group into the benzene ring, that is from benzene, if you want to form this compound where the benzene is carrying a methyl group, So what is the name of this compound? This is toluene. So if you want to form toluene from benzene, then you may use the friedel alkylation reaction, where you need to give the halide of this alkyl group. Here you can use methyl, you can use ethyl, whatever you want. If now I am converting benzene into toluene, so a methyl group has to be introduced into the benzene ring. So here I will give CH3Cl. Okay, now you may use CH3Br or CH3I, whatever you want, but with this you also need to add anhydrous AlCl3, aluminium chloride, and this overall reaction is called Friedel-Crafts alkylation reaction. Now what is the role? First of all, what is the role of anhydrous aluminium chloride, and then what is the mechanism of this reaction? Now what is the use of anhydrous and aluminium chloride, and why are we using anhydrous AlCl3? Why are we not using hydrated AlCl3? Now you know the hydrated AlCl3, this is AlCl3 comma 3H2O. This is hydrated aluminium chloride, and what happens if you heat this compound, then this aluminium chloride, which is a salt, will get hydrolyzed by its own H2O molecules, by its own crystal water, to form aluminum hydroxide and HCl. So if you give heat to this compound, then what happens? Aluminium chloride gets hydrolyzed by water. AlCl3 forms AlOH whole thrice and 3HCl. So our purpose will not be solved. We will not get aluminum chloride molecule. We may get aluminum hydroxide and HCl. So we shouldn't use hydrated aluminum chloride. We should use anhydrous AlCl3. First we need to give some heat to this compound so that this hydrolysis cannot occur, and aluminum chloride releases AlCl3 when you give heat to this molecule above 100 degrees centigrade. Then H2 actually vaporizes to form heat above 100 degrees centigrade. H2 releases as H2 vapor to form anhydrous AlCl3. Now we need to consider what is the role of aluminum chloride. Now aluminum chloride is a Lewis acid. Aluminum, the electronic configuration of aluminum is 1s2, 2s2, 2p, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, then aluminum. So the atomic number of aluminum is 13. So the configuration is 1s2, 2s2, 2p6, then 3s2, then 3p1. So the outermost shell of aluminum is a third shell, and all the electrons present, that is all these 3 electrons present in aluminum, are valence electrons. So the configuration of aluminum in aluminum chloride is 3s2 and 3p1. Now what happens? One electron jumps from 3s orbital to 3p orbital, giving rise of 3 unpaired electrons. So 3s1 and 3p, 3s1 and 3p2. So 3 unpaired electrons are there, which can make a bond with 3 chlorine atoms. So this unpaired becomes bond pair by the unpaired electrons of 3 chlorine atom to form AlCl3 molecule, and then still after formation of aluminum chloride, this pz orbitals remains completely vacant. Okay, so if aluminum wants to accept lone pair or paired electrons from other molecule, it can accept that paired electrons and can accommodate that paired electrons to its vacant orbital. That's why aluminum chloride is a Lewis acid. Now what are Lewis acids? Lewis acids are those which can accept lone pair electrons or paired electrons from others. Okay, so aluminum chloride actually acts in this particular Friedel-Crafts reaction aluminum chloride or anhydrous aluminum chloride acts as a Lewis acid which accepts electron from chlorine, which accepts lone pair electron from chlorine. We will see that next. Okay, so here we are going to make the mechanism of Friedel-Crafts alkylation reaction, where we use CH3Cl and anhydrous AlCl3. Now already I discussed that aluminum chloride, being a Lewis acid, will accept lone pair electron from the chlorine atom of CH3Cl. Now if we do not use aluminum chloride, still the reaction can happen. Benzene has pi electrons, as I discussed earlier, that this benzene has pi electrons, and that pi electrons are not tightly held by the carbon atoms, so that pi electrons can easily be moved towards the positive center. Now between CH3, in CH3Cl, CH3 has the plus I inductive effect. Plus I inductive effect means the tendency to push the bond pair electrons to the other atom, and here chlorine also being an electronegative element, chlorine has the minus I inductive effect. So what happens here, actually the bond pair electrons between the carbon and Cl in CH3Cl molecule gets pushed by the CH2 group and shifted towards the chlorine atom, making this bond partially polar, okay, where chlorine is having some partial negative charge and carbon is having some partial positive charge. Now that pi electrons can come, pi electrons of benzene can attack to this carbon and make a bond with this carbon, but to raise the rate of this reaction, to increase the rate of the reaction, actually aluminum chloride is used, where aluminum chloride accepts a lone pair electron from chlorine to make a coordinate bond. Now chlorine, the valency of chlorine is 1, so it cannot make a bond more than 1, that's why this bond has to be broken, okay. So when this bond breaks, a CH3 plus is formed, CH3 plus. Here in CH3Cl molecule, carbon was partially positively polarized, but after this a CH3 plus, which is a perfectly electrophile carrying a positive charge, is formed. So by this method or by this reaction, an electrophile is generated. Now this benzene ring can, the pi electrons of benzene can easily attack to this positive center to make a bond, and a carbocation is formed here. The carbon bonds breaks from this carbon, that's why here this carbon carrying a positive charge, and the CH2 group enters in this carbon where a hydrogen atom is already there. Two hydrogen and CH3 cannot lie in the same plane, as steric hindrance may occur. To avoid that steric hindrance, one goes to the above the plane, and the other, that is the hydrogen atom, goes to below the plane. Next what happens, hydrogen is removed by losing its paired electrons, and the benzene is formed, the hydrogen released as H plus ion. So here hydrogen released as H plus ion, and CH3 comes in place of hydrogen atom. So here the CH3 group actually substituting the hydrogen atom. That is how toluene is prepared, or toluene is produced. So this is the mechanism of Friedel-Crafts alkylation. Now what happens if we use CH2H5Cl and anhydrous AlCl3 instead of CH3Cl and anhydrous AlCl3, then what will happen? In case of, if we use here any alkyl group, I said earlier, if we use any alkyl group here, then the product will be the benzene, alkylated benzene. So if you use CH3 here, then the CH3 will go to this position. If you, instead of CH3, if you use C2H5 group, then the C2H5 will also be there. So this is the reaction. You can see here, from here you can see that properly, in proper way. Okay. I'm using this to see, to show you the board in more proper way. Okay, now you can see properly. Now if you C2H5Cl, that is ethyl chloride instead of methyl chloride, then you will get C2H5, then benzene or ethyl benzene. Now what happens if someone tell you that the reaction as propyl chloride is added in benzene, then what will be the product? Let us see through mechanism what happens if we add propyl chloride and anhydrous aluminum chloride in benzene. Then what will be the reaction? Here is, this is benzene. Now we are giving CH3 CH2 CH2Cl in presence of anhydrous AlCl3, and let's see what happens. Okay, from the first step, first step CH3 CH2, then CH2, then Cl will make some reaction with anhydrous AlCl3, where aluminum chloride being a Lewis acid will accept a lone pair electron from chlorine. Okay, so AlCl3, and here a coordinate bond will be formed, and this bond breaks to form a carbocation. Okay, so the carbocation forms here is CH3 CH2 CH2 plus. Okay, now this carbocation, this is a 1 degree carbocation, and you can see that no CH3 group is present there. Here a rearrangement occurs which is called 1,2 hydrogen shift or hydride shift, at hydrogen left this carbon by its by the negative charge by the bond pair electrons, that is H minus or hydride ion is shifted from this carbon to that. Okay, so this rearrangement, after this rearrangement a carbocation is formed where the middle carbon is carrying a positive charge, and this becomes CH2. By having this hydrogen it becomes CH3. Okay, so a carbocation is formed in which two methyl groups are present. Now methyl group has plus I inductive effect, so they will push the bond pair electrons to this carbocation. Now if someone has deficient in electron and some gives them electrons, then it will have a more stable condition. So CH2 group will show the plus I inductive effect and will make this carbocation more stable. So this one is called 1 degree carbocation, this one is called 1 degree carbocation, and this one is 2 degree carbocation. Now how can you understand which one is 1 degree or which one is 2 degree or which one is 3 degree? The positive, the carbon which is having the or which is carrying the positive charge, the carbon which is carrying the positive charge is directly bonded to only one carbon atom, then that carbocation is called a 1 degree carbocation. Here you can see that carbon which is carrying this positive charge is directly bonded to only one carbon. That is why this carbocation is called a 1 degree carbocation. And if the carbon which is bonded, which is carrying the positive charge, is bonded to two carbon atoms at the same time, then this carbocation is called 2 degree carbocation. And if the carbocation, for example here, this carbocation, the positive charge is here and surrounded by 3 CH2 group. This carbocation is having 3 carbon atoms attached or bonded with the carbon which is carrying the positive charge, and this one is called 3 degree carbocation. Okay, now here CH2 group will show the plus I inductive effect and reduce the positive charge of the carbon, and here 3 CH2 groups are there which will show their plus I inductive effect. So here the positive charge will be more reduced than the former, and then this 1 degree carbocation. So we can say that 3 degree carbocation is more stable, or more stable than 3 degree carbocation is more stable than 2 degree carbocation. and 2 degree carbocation is more stable than 1 degree carbocation. So here we can see, here we can say that 3 degree carbocation is more stable than 2 degree carbocation, and which one is more stable than 1 degree carbocation. So what happens for this reaction? When this carbocation is formed, then benzene comes and attack to the carbocation, that is attacks here, and the resultant compound is benzene, which makes a bond with a carbon, this carbon CH, and which has two CH3 groups attached with it. So here a CH3 and here also a CH3 group, and that compound is called the cumene. This compound is named as cumene. So this is the FRIEDEL alkylation reaction. Next we will see the reaction mechanism of FRIEDEL acylation reaction. Okay. Let us see what happens when we need to add acetyl or acyl group in benzene ring. Now acetyl chloride is CH3COCl. This compound is called acetyl chloride. CH3, C double bond O, single bond OH. This compound is called acetic acid. Acetic acid. If a Cl is there instead of, if a there instead of OH, then this compound is called acetyl chloride. Acetyl chloride. So this group is called acetyl group. CH3 C double bond O. This group is called acetyl group. Okay. Now if you need to enter this acetyl group into the benzene ring, you need to, this is one is also called FRIEDEL reaction, and this is FRIEDEL acylation reaction. If you need to enter this acyl group or acetyl group into the benzene ring, you need to take its halide, that means chloride, CH3COCl, acetyl chloride along with anhydrous AlCl3. The reaction mechanism will be the same. So the reaction, the acetylation reaction is benzene, then CH3COCl in presence of anhydrous AlCl3 to form benzene. COCH3 will be there, so C double bond O CH3. So this one, this formed is a ketone where a carbonyl group is there, and one side of the carbonyl group is a phenyl group, and in other side there is a methyl group. So it is a methyl phenyl ketone, or the compound is named as acetophenone. So the name of the compound is acetophenone. Okay. So reaction mechanism will be same like FRIEDEL alkylation reaction. CH3 C double bond OCl will react with aluminum chloride when chlorine is donating its lone pair electrons to aluminium, and aluminium having a vacant orbital accepts that lone pair electrons to make a coordinate bond with the chlorine. Now when a bond is formed here, chlorine cannot make two bonds at once, so that bond has to be broken to form a electrophile. When a bond comes out from this carbon, so CH3C double bond O plus, this electrophile is formed. Okay, now benzene comes and attacks to this carbon, to this electrophilic center to form the compound. Here a positive charge, that is because the bond is broken from this carbon, so here this carbon will carry a positive charge, and the COCH3 group goes to the above the plane, and the hydrogen which was present remains in below the plane positions. Then the hydrogen is removed as H plus ion to form this compound COCH3. So where the hydrogen atom was present, now the COCH3 groups comes here. So this one is also an electrophilic substitution reaction, but the electrophile is COCH3 or acetyl group. That's why this is called FRIEDEL acetylation reaction. Okay, so this one was the electrophilic substitution reaction of an example of electrophilic substitution reaction of benzene. Next we'll see what happens in nitration reaction. Nitration is also an example of electrophilic substitution reaction. Okay, so let's see what happens when benzene is nitrated, or how this reaction happens. Let's see the mechanism of the reaction. So when benzene is treated with a mixture of concentrated acid HNO3 and H2SO4 at a temperature of 50 to 60 degrees centigrade, a nitrobenzene is formed, benzene carrying a nitro group, and this compound is called nitrobenzene. Okay, now let's see the mechanism of this reaction. The nitrating mixture, actually the mixture of nitric acid, concentrated nitric acid and sulfuric acid are prepared separately in a round bottom flask, giving temperature at 50 to 60 degrees centigrade. For nitric acid, the solution becomes brown, when nitrogen dioxide is formed along with NO2 plus ion. Okay, so the reaction mechanism is that nitric acid, we can write nitric acid in this form HONO2, that is HNO3, and here sulfuric acid, H plus comes from sulfuric acid, H plus that comes from sulfuric acid, concentrated sulfuric acid in the reaction mixture, and that oxygen of OH group gets protonated by making a bond, making a coordinate bond. Oxygen has lone pair electron, you know, in OH group, and H plus hydrogen atom is 1s1, that is a single electron is present in hydrogen atom. So hydrogen, normal hydrogen contains 1 electron and 1 proton only. Now if you remove that electron from hydrogen atom, then H plus ion is formed, which contains only a single proton and nothing else. That's why H plus ion is also called a proton. And that hydrogen atom, electron was present in 1s orbital. 1s1 was its electronic configuration, and when the electron is released, then its 1s orbital becomes completely vacant. So if someone donates its lone pair electrons to H plus ion, H plus can accept that lone pair electrons and can accommodate that lone pair electrons to its vacant orbital. That is why a coordinate bond can be formed between oxygen of OH group and H plus ion. Okay, now when this coordinate bond formed, it becomes H2O bond NO2. Since oxygen used up its lone pair electrons, oxygen is having a positive charge here. Next, this releases as neutral H2O molecules. The bond breaks from this nitrogen atom, so NO2 plus is formed. Now nitronium, NO2 plus is called the nitronium ion, which is the generated electrophile. Now that electrophile acts with the benzene ring, reacts with the benzene ring. Okay, so this one is called the nitronium ion. Nitronium ion, which is the generated electrophile. Then benzene comes and reacts with nitronium ion, which is the electrophile, to form nitrobenzene. The pi electrons attached to this nitronium ion to form this carbon having the positive charge. It goes to the above the plane, and the hydrogen remains in the below the plane positions. Then hydrogen is released as H plus ion benzene, and this nitro group is present there instead of hydrogen. So here we can, all these 6 positions are equivalent, so we can place that nitronium or the NO2 group in any one of the position. So this compound is formed, which is called nitrobenzene. Okay, so this is how the reaction occurs. So you see the reaction mechanism of 2 reactions, so namely Friedel-Crafts reactions and nitration reaction. Next day I will have some other reactions to show you the mechanisms of some other organic reactions. Along with, we will also discuss about the orientation of the groups present. That is when benzene, in benzene the nitration occurs and nitrobenzene is formed. Then, but if there already a nitro group is there, if we react nitrobenzene, if we make a nitration reaction of nitrobenzene, then what will occur? Then the NO2 group, where the NO2 group will come, in here, here or here, that will depends upon the group, the substituent which is already present, that will direct the incoming electrophile to go to either positions. These 2 positions, this one is called ortho position, this one is meta, and this one is para. So either the entering electrophile comes to ortho or para positions, ortho and para positions, and at that case 2 isomers are formed. One is ortho isomer and the other is para isomer, or they may enter in meta position. That will most depends upon the orientation of the substituent already present. So next day we will discuss about the orientation of the substituent. Okay, for today, goodbye.